In this problem, a 15,200 kilogram lunar lander is descending onto the moon surface with a velocity of 2 meters per second when its retro engine is fired. So, if the engine produces a thrust T for 4 seconds, which varies with time as shown, and then it cuts off. So, we have to calculate the velocity of the lander when time is 5 seconds. And we have to assume that it has not yet landed and the gravitational acceleration at the moon's surface is 1.62 meter per second square. So first of all, let's talk about its formula. So the formula for linear impulse and moment is g1 plus integration of impulse from t1 to t2, that is equal to g2. So here g1 and g2 is the linear moment, and g1 is equal to mv1 and g2 is equal to mv2. And we know that this lunar lander produces a thrust that is basically the variable thrust, and it is acting vertically upward. So we have to integrate variable thrust from 0 to t, and we also know that the lunar lander has some weight, so weight is acting vertically downward, so we have to also integrate weight from 0 to t, and linear moments are also acting vertically downward. So the equation for linear impulse and moment is mv1 plus the impulse integration of impulse from 0 to t, that is equal to mv2. So you see we can write uh, integration of weight from 0 to t minus integration of variable thrust from 0 to t in place of the impulse, and we have to integrate time from 0 to 5 seconds, so it becomes our equation 1. And you see here m is the mass of lander, v1 is the initial velocity, g is the acceleration due to gravity, and v2 is the final velocity that we have to find, and tt is the variable thrust that is acting on the lander. So if we see this curve, so here we observe that from time 0 to 2 seconds, the thrust increases linearly with time, and when the thrust reaches 45 kilonewtons, so the thrust remains constant from time 2 to 4 seconds, and then from 4 to 5 seconds thrust becomes 0. So you see we have to integrate variable thrust from 0 to 2 seconds, 2 to 4 seconds, and from 4 to 5 seconds. And also you see here the term, the integration of variable thrust from 0 to 5 seconds represent the area under the TT curve for the time interval of 0 to 5 seconds. So if we take a look at 0 to 2 seconds, so here the curve looks like a triangle. So the area of the triangle OAC is 1 divided by 2 multiply 45 kilonewton. And to convert kilonewtons to newtons, so we have to multiply it with 1000 newton divided by 1 kilonewton. So we get the variable thrust from 0 to 2 seconds, that is 45,000 newton seconds. And from 2 to 4 seconds, here curves acts like a rectangular shape. So the area of rectangle ABCD is equal to 4 minus 2 multiply 45 kilonewton. And we have to also convert kilonewtons to newton. So here the variable thrust is 90,000 newton seconds, and from 4 to 5 seconds the variable thrust is 0. So if we substitute these values in equation 2, so the variable thrust from 0 to 5 seconds is 1,35,000 Newton seconds. So also we have to put the value of mass, the value of the acceleration due to gravity, the value of initial velocity, and the value of variable thrust from 0 to 5 seconds in the equation 1. So it becomes 15,200, that is the mass of the lunar lander, multiplied to that is the initial velocity, and again this is mass and this is the acceleration due to gravity on the moon surface, that is 1.62, and we have to integrate it from 0 to 5 seconds, and this is the integration value of the variable thrust from 0 to 5 seconds, and this is again mass, and we have to find the final velocity, that is v2. So when we multiply this, so we get 24,624, and when we integrate it, so we have to multiply it with 5 minus 0, so we get the our final velocity, that is 1.2184 meter per second. So the velocity of the lander at 5 seconds will be again 1.2184 meter per second.